Yeah. So I have about 10, 50 or 15 minutes or so. So basically, I'm not a filtering expert or anything like that, or I haven't worked in data assimilation also. But my first stint with the weather people were in Hong Kong, where people just came and asked me, can I help them in doing some air pollution model? Okay, so basically they were the weather people and they wanted to fit the air pollution to do an online estimation and forecasting there, and predict for the government, because the government has the strict rule. If the air pollution goes above certain level, they close down the school, etc. They actually do that there. So I mean, I just started working with them, and then we sort of use some statistical techniques of multiple time series using the air pollution things, and then basically the model what we have got in 1998, I have been told that they have been using this model for 12 years or so after, with some improvement later on. I mean, but it has been used, in fact, online forecasting. So I was happy to hear that when I went 2010 there. So that was my first state, and then on and off I have been going into this kind of things and learning more and more. But here, basically I'm as you see, I'm more probabilist, as you are saying. So I've started working with one of my students here, who is here already, Runangshu. He has submitted this thesis in ISI. And what we are doing here is, as you all know about the MCMC. Basically there is, you sort of start selecting samples from the, try to select the samples from the target distribution, but you cannot do that. So you start using some, other distribution, for example. So the idea is to generate them for large dimensional data and for large number of samples, but effectively how to do that, when to stop, and when you think the target distribution reached, those are the questions remains always challenging. I mean, so here we denote this by basically saying psi is the target density, let's say, and we will discuss this by a toy problem really. And so proposal density, as you would see that one would take normal or any kind of nice densities can be taken as a proposal density. But the steps comes back to generating sample, start with any x naught, generate sample y from p dot x naught, and then use Westerbork Hastings rule, and use that psi py x naught with the minimum of that, with that probability, accept that nth one, otherwise reject. So, okay, sorry. So for large n, we believe, let's say we believe that xn is sort of approximately psi, okay. That's the target distribution, we think that it has been reached. So the limiting distribution basically doesn't depend on, so the Markov chain theory would tell you that limiting distribution would not depend on this. So now suppose you take pyx is the normal x sigma square. So the trick is that if you choose large sigma square, then you sort of explore more and more regions. We all know that MCMC sort of gets stuck if it is sort of in a well situation. So you sort of tend to use the large variance so that you can jump off to some other with positive probability to other wells, etc. And then but then the fewer samples would be selected if the larger variance is there. On the other hand, if it is smaller variance, then you would tend to have more samples, but you would not go from well to well. You would stuck in the one well situation. So that has to be, there is some optimal policy has to be chosen there. So as I think along the line what Raman was talking about, I'll show some of the actually assumptions what MCMC people have been doing there. In 2001, Harry actually started the, one of the paper probably he has mentioned the adaptive MCMC, where you sort of vary the variance depending on your previous data. So how much you have already accepted, and then whether you are stuck in one region, you want to explore more. So you sort of go on exploring depending on, so that's sort of things called adaptive MCMC. So as I said, that idea is to change the proposal kernel itself, that means the PYX. It would not be just PYX, it would be PNYX as you go along. Okay. And then some more papers, of course, along the line. We will mention few of them. Roberts Rosenthal came up with the following theorem that if psi is stationary, so that as I think this is the sort of similar condition what Raman was mentioning, that supreme of p theta n plus 1 minus p theta n x, it is actually consecutive, the diminishing adaptation type of theorem. And then, so the theorem of Roberts Rosenthal guaranteeing that some kind of time stationarity as xn moves along this changing proposal density. So that's what they have done. So here we will discuss a toy example really. I think the idea came from Peter Green, who was in Bristol that time when we talked about. So this is simple. You start with x naught, theta naught. Here theta naught is a proxy for the variance. Theta naught is the variance. So where you start with a y, as I said, the normal xn1 theta n1, and then accept the new point with image probability, right? So if the new point is accepted, then you put xn equal to y, otherwise just move along, okay? And then you update the theta like this. So theta n would be basically, if you accept more, as you see that xi n here, xi n is the acceptance region. So if you put xi n to be 0, then you would be reducing the theta. If xi n is 1, p is actually between 0 to 1. So here, so xi n is 1, you would be increasing the theta. But original suggestion of Peter actually was little more. Peter was saying that why don't you put xi, instead of just one of them, you just put the average of them. Take whole history of acceptance rejection thing, and then put here Sn by n, Sn being the summation of xi n. Okay. So, and then you move along that n goes to n plus 1, and then do the same step from step 2. So ideally, this is basically some kind of, we wanted to think about in terms of stochastic approximation algorithm in the sense of, so here our sort of goal was really try to compare, what my student had done here is really wanted to see that if we sort of use the adaptive algorithm and non-adaptive one, how does it compare, whether you reach the target distribution faster, whether you reach at all there, those kind of questions are really into consideration here. So what we have done, instead of looking at the discrete part, we actually use this stochastic approximation technique to put into diffusion, approximate this by diffusion framework. We approximated xn plus xn as xn at I plus 1 over n, and then put this as a this equation, which is there, and then xn at t is this one, and then go along with xi n of I plus 1 over n like this. We use these probabilities and use the Metropolis Hastings probabilities at these time points. and then go along with the thetas now. Thetas would be approximated like this one, and the one important variation we have to remember, this Pn, this Pn has to be also approximated like this. That means Pn would be eventually going to 1, as you see, because if you are doing finer and finer, you would be really talking about how far it is. That means everything would be, you see that xi n plus 1 would be approximately always near 1. So that's why Pn also has to go to 1. So this is the rate we have seen that where you at least get some non-trivial density, otherwise you don't. I mean. So first theorem we get basically after doing this approximation scheme, we get the limit process. We have started with yn jointly, xn and xnt and theta nt would give rise to would converge weakly to this one, where byt would be theta square t over 2 psi prime xt over this, and it's a 2-dimensional. And the second part sigma is, you see that sigma yt, that means the diffusion coefficient is singular. Okay. So the whole adaptive MCMC setup, if you have, this is just toy example, as I said, the one-dimensional, but if you do multi-dimensional thing with the, that means psi is the target density for multi-dimensional distribution. So basically you would be getting some kind of gradient here, so you will be getting the by as a that k dimension, k plus 1 dimension, and then you will be getting this sigma also just singular. So that's the important part, I mean. So we have to deal with the singular diffusion there. So the idea is that the toy, in this toy example, we will basically try to argue that even if you have a singular diffusion, we actually can use the we can actually use the Hermander hypoelectricity type of condition to show that the support is actually full and there exists the density. Okay, so that's the idea. So here in the toy example, actually, as I said, I will explain this in the toy example. We'll show that we'll see that in this toy example that when the target density itself is normal, okay, then you will get this one, and in this case you can, and also you could see that if the adaptation parameter is constant, that means if you look at the standard MCMC, that also can be approximated to the diffusion, and you get one-dimensional Ornstein-Uhlenbeck process. Okay, so instead of this 2-dimensional thing. So basically our aim would be to compare these two, standard MCMC and adaptive MCMC, how these two approaches to the target density. And we all know that Ornstein-Uhlenbeck process has the target density to be normal, I mean, which is stationary distribution of this. So what we basically proved, we proved the tightness condition, and we've sort of proved the Hermander hypoelectricity condition for this one. I mean, we need to tie a few details in there for general case, and finally we sort of showed that this is one simple example, as I said, that in this case we could show that exactly moments, limiting moments of xt is this that of normal. Okay. So that means then you could use the moment generating function to show that this target density is actually normal. Okay. So I mean, ultimately how do I compare these two, standard MCMC and this? Actually it turns out if I see these limits of this, actually we showed the limits, suprema of this is finite. In fact, we can show that this limit exists, limit of t, and the average of theta, that constant, if that constant is bigger than the theta naught, that means that for standard MCMC, then adaptive MCMC converges faster. Okay. If it is less than the theta naught, So this is the adaptive case, right? So you take r equal to 1, if you take the average, the limit of the average, if it is bigger than the theta naught, then you can show that it converges faster to the target density. And if it is less than the theta naught, then you would be slower than the target density. That's what, for simple case we can show it easily. However, if I take the target density to be, say, I give you the extreme, let's say Cauchy density. Okay, in the normal is very nice. We have all moments are finite and very nice distribution. Beyond plus minus 3 sigma, nothing is there almost, right? But on the other hand, Cauchy density, there not even the first moment exists. So basically, it's a heavy tail. So question is that, can we use this kind of MCMC technique to simulate from the Cauchy density or adaptive MCMC to do that? It turns out that if this one is finite, actually our method would not work, our simulation also say, if this one is finite. So we have to develop something new to say that this averaging should actually be infinity. Actually, we don't want it to be very fastly converging. We want it to slowly converge so that it can go to different places. Because to simulate Cauchy density, we need to go farther. So that's this particular method what we have done probably would not exactly work unless we show that this actually for Cauchy is actually infinity. This average is actually infinity. Okay. So some computation, but yeah. So it is basically showing the target density is normal. So we have done for discrete case adaptive versus non-adaptive, but so this is the p-value. We use some kind of, I think, Kolmogorov-Smirnov, right? Kolmogorov-Smirnov type of statistics to get the p-value here. We actually simulated the whole path and took the last one and simulated thousands of them, right? I think that's the way to have done. And this we have done for Cauchy. As you would see that Cauchy probably we have none of the method, neither non-adaptive nor adaptive works well, because 10 to the power minus 16 are huge difference. This is T2, this is also heavy tail. As you know, T distribution is 2 degrees of freedom, which doesn't have variance, finite variance is not there. And in the continuous version, that means if we simulate continuous version from the SD and adaptive SD, then we get this kind of results, and I'll quickly flip it through for the other. Exponential, this is sort of things actually we need for our theoretical things, we need the symmetric or at least two-sided things with some asymmetry can be allowed. But for exponential, we just wanted to try out our simulation techniques just throughout the other side. You can take the two-sided exponential, that means symmetrization of that also possible. But we just threw out the other side of the samples, we just took one-sided and compared it. This is just ad hoc actually we have done. And then simulation of again the Cauchy density from SD again. So it non-adaptive and adaptive. Actually, we have to agree, we have to sort of say that our technique of simulation only Eulerian method, so we could have done much better. We didn't know how to do the good simulation there, of course. So I wanted to finish it. Theta is the driving.
Less than the one for the non-adaptive case, then it's better.
Then it's worse.
Then it's worse, and then.
Yeah.
But is there in the actual algorithm, is there a priori way of calculating?
Average of theta, yeah. You can go along. That is, as you are moving, then you can take the average.
Yeah, so on the fly, but if I want to decide, should I use?
Oh, beforehand.
Yeah.
Beforehand. That's the good point. That means that mainly basically if you want to do the theoretical calculation beforehand, that means you can actually do in the back of the envelope calculation beforehand, that means theoretically, and then run the algorithm. Then run the algorithm. Yeah, that's it. Because theoretical results are there, so you can compute that separately, then run the algorithm. Yeah.
The fundamental goal of MCMC is simply the following. I give you a polynomial distribution sitting way out there. I give you a function f which happens to be integral with respect to that, called the integral lambda, and I want to approximate lambda. You have a target density. If I give you a function that happens to be integral with respect to that, and you're generating a non-stationary Markov chain, what's your estimate?
No, I'm not. What non-stationary is.
You're generating an adaptive sequence of random variables.
Right.
Which don't have a constant transition.
Oh, right. Exactly. That's the kind of algorithm started in 2001. I mean, they were giving some kind of diminishing adaptation criteria. That means, as you go along, you are not making very many. That means, difference between the movements are getting slower and slower. Then.
So do you have a consistent estimator number one?
Mm-hmm.
Number two, do you have any idea as to how bad the error is? Is it like 1 over square root of that?
How bad the error is actually, what we have done is that we have approximated this in the continuous time totally.
So you have a limit theorem for the
Continuous time. Yeah, continuous time. So in the continuous time, our error would be given by this, how this average of theta goes. That means in continuous time, what we have found that the integral of theta is ds. So 1 over t of that will sort of give the error. E to the power of minus of that basically is the error. That's the rate of convergence to that. So in discrete time, I think Harrio and others, Roberts and Rosenthal, they have sort of had some approximation idea.
what is precisely your estimate? I give you a function that is
empirical average converges to everything if the f is complex. And under the conditions of reducing adaptation, thus the hypothesis.
Do you have a sequences? So maybe we can have
Should I?
Let's see, yeah, right before lunch, that makes me nervous. Okay, so this is actually a nice talk to give today because we talked sort of over on one end of the spectrum, we have and then I think over here we have three, but both of these talks reference something about like trying to figure out something from you're basically hidden. You have something that's hidden, right? Well, I want to figure out hidden parameters, especially like the hidden parameter, and this is me. You know, and this is actually probably me. This is all very computational. Okay, so it's using the ensemble Kalman filter, local ensemble transform Kalman filter, which is just too big of a word. But and this is joint work with Tom Belsky and Louis Mitchell at various places. And yeah, I'm glad to be here. So this is fun to give a talk in India. All right, so here's the goal. This is some of the stuff we've done. Basically implement local ensemble transform Kalman filter. That's the last time I'm going to say that. LETKF to actually look at parameter estimation for, you know, and parameters are essentially, we'll talk about this in a minute, but essentially stuff you cannot resolve. And you want to do this correctly. And we talked a little bit about this yesterday with asking, you know, what, you know, in the afternoon, someone was asking about, you know, coarse model, but your model can only see what it can see, right? What it can resolve. So, and what we considered in this work, just that was sort of an initial test consideration of implementation of these algorithms, which are not necessarily new. You know, they've been used by a couple other people. But we ended up just doing a small tweak to get them to work, sort of in a local sense. And we looked at a single scale, which I'll explain, a multi-scale, time, and various sort of multi-scale aspects of this, and then a little stochastic aspect of this too. And then the longer-term goals are actually to incorporate real-world observations, which we're working on, which has its own problem, obviously. And then the long-term goal is actually to just push this up through the sort of hierarchy of models, which I guess is always the goal in computation, just push it up. Next would be like sort of the speedy model, which is a nice sort of mid-range test bed. All right. So this is sort of the obvious slide. We all know that everything depends on parameters, but basically this is if you have a giant model and you get your parameter wrong on a single grid element, essentially you're looking at your atmosphere incorrectly. Your atmosphere is a single attractor, right? That's probably not good. So getting your parameters correct is essential, right? So I kind of spell this out here, but accurate and predictive modeling requires a faithful representation of physical parameters. And this has been done as an art form in large models by tuning, right? It's got the technical term of parameter tuning, but match your model with the known data, and it doesn't quite work, tune your parameters. So this is sort of an ultimate goal here is I think we can do a little bit better than that. I guess it makes, I guess I shouldn't, I'm not saying that's a bad thing. It's actually worked really well, parameter tuning, but it's not, I don't know, it doesn't feel intuitively, doesn't leave me warm and fuzzy. I don't know. I can't think of a good way to put this. All right, so.
You're in India, right?
I do. So all right, that's the end of this then. So this is just, I pulled this off of Wikipedia. This is just to show really the time scale, just to get an idea. Right, there are grid scales involved. There's atmospheric, turbulence. There's, I think this is actually just showing atmosphere. These are winds. But then down below we've got ocean currents, and those are different time scales and different length scales and everything. So that's the ultimate goal, is to actually pull out the subgrid scale and fast time scale physics that are parameterized, and to get those right, or as right as possible. I mean, let me put it that way, to get those as correct as possible. And as I mentioned, model tuning is sort of that's been sort of a big part of actually climate modeling. And so the ultimate, what I'll show here just briefly is LETKF methods can offer sort of an efficient way of tuning your parameters when you have, and the key aspect is when you have like a spatially or maybe temporally varying parameter. Okay, like basically think of a temporally or a spatially varying forcing, and that's what we end up looking at specifically here. All right, so what's that? Okay, that's a holdover. That's local. That's a holdover from the title, because if you spell out local ensemble, and then you put local as well in the same sentence, it just didn't work. Yeah, local. Sorry.
Local refers to the locality of the observations, not
yes.
the parameters.
Oh yes. Oh, I see. Yeah, I'm specifically talking about when you're looking at like a gridded simulation, local, grid-wise.
Each grid point has its own parameters.
What's that?
It's not like each grid point has its own parameters.
It could. Each grid point could have its own, likely does have its own, you have a system of equations on every grid element. Yeah. Yeah, exactly, yeah. Yes, there you go, yeah. And so we want to do this, we don't want to sort of get an average of this, we want to get specific.
No, I'm not, but I'm saying in practice, actually, does it happen?
It depends, I don't know, yeah, it depends on the model, right, where you are. Right. Not that our model involves elevation, but. So I don't know if anyone's actually gone through a cartoon of the ensemble Kalman filter, so I put this in here. This is our true system. It's a sine wave. This is basically, I think I've switched to z's later, but basically our state, we have one-dimensional state, and it evolves through time. the ultimate low dimensional system. So this is essentially what we do in our model. Essentially, we take the truth and we perturb it a little bit to get our observations. I mean, we're not using we're not using a large realistic model. We're just sort of doing a proof of concept. But we perturb, get your observation, which is a noisy observation from the truth. You never really get the truth anyway it goes. And then you initialize your model, and sort of around here, and the model, you propagate it forward, and it ends up here, and then you find the ensemble mean, and then you can form a covariance matrix based on that, and a covariance based on the noise associated with the observation, and minimize an objective function, and bam, you have a new initialization, and you can sort of take the posterior of that and run a new ensemble from that. This one seemed to converge pretty quickly, but not necessarily that quick. So that's what we're doing, except for we have many grid points and we're localizing the process. That's really all that's going on. Yes, yeah. And actually, in fact, yeah, it is in most of the examples. We did actually look at a little stochastic forcing as well on top of that, but ultimately the forcing is a sine wave with various amplitudes. So what we talked about back there was the ensemble ensemble Kalman filter, and if you had some localization, this is the you can get your local covariance matrix, which is just going to be k by k. That's sort of, and we could talk about that. I am bumping up against lunch, but that's the reduction in dimensionality that really makes this work much nicer and it makes this tractable. So that's instead of. Oh no, sorry, K is the ensemble. K ensemble. Yeah, so K is just. It's formed from the perturbation from the mean of. Oh no. This is in general. We've moved past. This is sort of the general system. Yeah. So this is for.
The dimensional PP should be that of the model, no?
No. You're thinking like n by n, right?
Yeah.
No. But you can if you take. Yes. But yeah. So you can form. What is it? The background. K ensemble vectors, where each of these is basically x I minus x background. So this is going to be essentially big by k, right?
Yes.
And so x, let's see if we get this right, xb transpose, xb should be k by k, being defined as pb, I think. Is that? Yeah.
We do the opposite. X trans, x.
Oh, is it? Maybe I got that.
The dimension is the dimension of the state vector, and the rank is k.
You're saying it n by. Oh, did I get? Yeah, let's make. I may have gotten that. I know the rank is definitely it's k minus 1. In fact, I think.
K is number of ensemble forces, means that k is number of columns.
Yes.
So PP should be the size of the state and times n.
Mm-hmm.
As maximum the rank equals to k.
Yes. Yeah. Rank. Is it k minus 1? But yeah. Okay. Yeah. Okay. We'll make sure that's right. But what we did above here was actually just minimize the objective function here based on however we write. Maybe I will rewrite that correctly. But using covariance based on the essentially your model and covariance based on observations. There. So. We're exploiting sort of the dynamics in this, but no. Are you talking about? What's that?
As I understand it, there's a spatial structure.
Oh, yeah. Oh, for this matrix themselves. Just the fact that it has a certain rank. I mean, that's all I'm.
This is relevant, and there's a lot of work going on in how you split up, say, variance.
Oh.
To a low rank part.
Oh, I don't know. That would be interesting to talk about. I don't know, much about that. Yeah.
What is the localization?
What's that? So the localization is just going to be some radius around. So you can just use, some radius around a grid point and just look at the do your update based on that. So a much smaller dimensional update.
How do you decide that small by data?
That's up to you, and that's actually something we'll talk about. Yeah, that's one of the free parameters. Was there a question?
Yeah. This question, how many components are the covariance depending on which observation? All y?
That would be, you could take all of them, but if you're going to do it locally, you can hone in just with matrix algebra to hone in on the local portion.
And the same y's are used when you're
Same. Say again.
the y's observations, same observations are used when you are using y.
Oh, yeah, the same observation at that time step, the same observations, but again, you may only be using these 9 observations.
And you are using, I'm just trying to understand that what are the observations used for the calculated covariance and what are the observations used for the y?
Oh, the observations used for, sorry.
Because you see, I'm just saying that you are using the data twice, basically.
Oh, no. Right. The observation and only comes in here. This covariance matrix is using only the mean and the ensemble mean and then the actual the difference between the ensemble mean and the ensemble vector. Is that, I don't know.
And the R part.
R is determined by just, it's probably constant, it's basically constant in ours. It's just based on the noise from the observations itself. So in a more realistic setting, I'm not entirely sure where that comes from, but it actually could evolve in time. I don't know, maybe Alberto, maybe you've even worked with that.
And just it reflects your knowledge about the traditional network. In the most simple case, it's just instrumental noise.
You will pass slide 3 for sure. Yeah. What's that? Yeah. 3D. Right. Oh no. 3D. Oh, I'm not. Yeah. Sorry.
So in principle, you minimize objective function. In practice, you don't minimization. So it's not.
Right. As I. Lunch, I'm going to move on quickly. Okay, so to pull in the parameters, this is sort of an interesting step. You can just augment your state space. And so with the update we talked about, you can just, if you want to update space just as in terms of space, all right? And so you update space just by this using the ensemble Kalman filter, local ensemble Kalman filter. And then the parameters you can actually, this is sort of a typo. You actually will include, you'll actually look at the objective function, but for this entire augmented vector. And there's actually a little thing in here. You should get a new ZA and PA, and then you can just pull off the updated parameters from that. And that's really what's going on there. So really, the state of your system, if the parameters are changing, that should be informing you about, using the observations. You should be able to see that when you sort of pass everything through the objective function and minimize.
Makes the problem nonlinear.
Well, right, but the operator,
All I'm pointing out is that you think of the parameter of the states and augment the state space. Is the problem nonlinear?
we're still just approximating things. So, so all right, this is the system we use. This is basically just looking at sort of Lorenz's Lorentz 96 model, which is, has a fast component coupled to a slow component. And you can, I think we used a couple different systems, but essentially, if we actually looked at no coupling at all, just the yellow band with about 40 sites. And then if we coupled it, we actually cut it down to about 16 sites, just if you're curious. This is each xi, each yellow dot is this is the state for xi. This is how it evolves in time. Then if you couple, I didn't put this in here because it looks fairly similar to this, and you can couple based on essentially coupling strength, and you can add in essentially an epsilon term for how your time scale difference. That's really where you can have the same time scale, you can have various different time scales, depending on how these are evolving. So this is where your hidden physics comes in. So when I say fast coupled physics, it's coupled at various strength, it's moving at different speeds. That's
The little white dots around there are another Lorentz 96 model?
it's very similar to this equation. Yeah, I just didn't put it in for simplicity and because I knew I'd be bumping it. Exactly. This is right here. This is another set of equations. dy dt. Yeah, and then they couple back in. Yeah, and it's actually, I believe we just use like a one-way coupling. Actually, it does not feed back into the fast system. And this is the actual forcing. There's a mean, I think about 8, but essentially there's a sinusoidal portion, and it's got a period that's essentially, if you spread out all of your sites, if you unroll this, it's got a period that's just essentially as long as your sites, so a period of 16 or 40 sites. And this is just to show you, actually, it does work relatively well. If you actually do use localization, this is the sort of localization that we use. Oh, yeah, good question. The actual sign, the amplitude of the sign, alpha.
Just have 2 parameters.
Yeah, and then actually,
They're not local parameters.
no, actually, that should be. Yeah. What's that?
You could pick fi itself.
Yeah, I could pick fi itself, but what we're actually doing, it's not a local parameter, but at each site it has a different value. Because this sine wave, it should have a different. Yeah. Right, Bill.
Is it C and alpha?
No. No, it's just alpha. Are we quibbling about colors here? Oh no. Okay, good. But go back. Yeah.
So P.
Yes.
What's the dimension of P in your problem?
It'll vary, but essentially,
In your problem, that is just
right.
Is it 1?
Yeah. This one, we're just looking at estimating one single parameter, and then, but wait, there's, yeah. Just think of it about tacking on alpha. Yeah. Right. So, but fi varies across space. Okay. Yeah. That's all. Yeah. Fi changes. Yes. So what we're estimating here is actually is the amplitude of the sine wave at that site, and that was sort of incorrectly colorized. And so it does depend. It depends pretty strongly on localization. So essentially, if there are 40 sites, and so if you take a radius of 20, you've got the whole system, right? So if you take a radius of 20, you actually find, well, luckily you do find the mean. You find f0, which should be what the ensemble Kalman filter sort of pulls out parameter-wise.
The same question.
Okay.
Your augmented system has been augmented by dimension 1, and you are estimating alpha. That's what you are doing here. You are not estimating alpha, you are estimating sine. So you are augmenting of just dimension 1, not 6.
What's that? Not what?
When you formulate the augmented system to estimate the parameter along with
Yes.
say,
Each.
augmentation has been done by dimension 1.
So I think I see what your issue is.
So are you estimating alpha? Like
no, I'm estimating the forcing parameter of that site, and that's the,
56. So you are
yes, yeah,
56.
yeah. I'm sorry, yeah, yeah, yeah. Yeah, I know. Yeah, yeah. I'm sorry. Yeah, yeah.
So you are estimating Fi, so you are augmenting the system as much as the dimension of the space, which is 50, 56 or 40 or
Dimension of the parameter.
yeah. And so and the y
but-
is eaten by the yellow there. The white.
Yes, the white is the truth.
The white is the truth. Yeah, yeah. And it's in.
Yellow.
No, it's not actually. It's hiding underneath the yellow. Right.
The white dot through it.
Yes. Yeah, yeah. It hides underneath. But so it does pretty well. Yeah. But
System is augmented by 40.
yeah. Yeah. Or how? Yeah. Exactly. So yeah, I'm sorry. You're right. And I'm thinking, yeah, you're looking for a single forcing, but you are augmenting by that many. Yeah. So that many. And there are strange, actually, finite size effects, which if you choose some intermediate and the local ensemble filter, okay, you just find the difference and normalize by sort of the ensemble, the original way I want to think about. And basically, as the forcing goes up, the ensemble, which is no localization, gets worse and worse in terms of its error, its root mean square error. And then if you actually compute the skill level, you can see 1 is actually as high as that'll go, and then it doesn't really have a lower bound, but you do pretty, with localization of 5, you actually do pretty well, no matter what strength of forcing for alpha you put in there for that sine wave. And then you do relatively well also if you just sort of think about fixing a localization radius. You do fairly well actually estimating the forcing parameter itself, Fi. So no matter what, no matter what really you put in for the actual amplitude. So does,
For this model, if the forcing temperature is pretty low, the system is a little bit
for this, for the general Lorentz? No, I think it's pretty chaotic actually.
It's not
Plus the sign.
so it's not easy.
Oh, okay.
Yeah. Okay. And this, let me, you guys, well, let me just skip and then go. So current work is actually just looking at some ice line models, which are possibly too low dimensional, but looking at implementing satellite data to see. It seems like a simple problem, but actually implementing real data is interesting. The question came up because reading another paper, which came across a problem, just to really point out that some of the parameters look at, basically the ice line in the Arctic don't seem to be quite right. And so the idea was maybe we can do a little better, using satellite data to actually estimate the parameters sort of in a computational way. And then the ultimate goals, the longer goals are, we're lazy, and one of us is an Australian, so he termed pestimation. They always shorten words. So lift the parameter estimation or pestimation to larger models. Speedy is sort of a good example, sort of an intermediate sized model. What's that? This is the technical term now. Oh, speedy. Oh, no, it is an abbreviation for, dear God. It's just an intermediate sized model, kind of a low intermediate sized model. And it is speedy in some ways. And actually this is what interests me. Just as I'll let you guys go in like half a minute, but I've noticed when I look back at what I've been doing for the last year, everything, I don't know how it happened, but everything I do involves parameters. So even in the topological data analysis, I look at parameter stuff. It's sort of interesting, and machine learning, and somehow these things have kind of coalesced. But this is really an online machine learning program. You're just always updating these parameters as you go. And so, we have a nice, very simplistic skill function, but something tells me the machine learners out there who deal with big data have probably come up with some interesting online methodologies for looking at this type of problem. So, for also maybe targeting observations, if you need to, if for some reason that certain localized, your parameter in a local area is not as good as it could be, but others are better. There's obviously a lot of work to be done. So. All right, thanks for.